Hi, I am Dennis Coronel, and today I'm going to present the article titled Autoencoder Network for Anomaly Detection in Wind Turbine. Today, I will present the introduction of this article, where I will explain the motivation and objective of the study. Next, I will detail the materials and methods used, including the wind turbines vibration database and the autoencoder method. Next, I will discuss the development of the anomaly detection algorithm and then present the result of times. Finally, I will conclude with the main conclusion and possible lines of future work. In 2023, the global wind energy section installed a total of 117 gigabytes of the new capacity, representing a 30% growth compared to the 2022, according to the Global Offshore Wind Report 2024. This reporting highlights that 54 countries across all continents participate in the construction of the new wind farms, with Latin America being to the regions with the highest growth, 21%, driven mainly by Brazil, with installed at 4.8 gigabytes. The main markets that led this and new installation are China, the USA, Brazil, Germany, and India, demonstrate their key role in the global expansion of wind energy. The wind energy face challenges due to unexpected wear and tear of key components, such as electric system, generators, blade, and gearboxes cause the challenging environment. This reduces the energy production by 10 or 50% on onshore turbines and 20-25% for offshore wind. In addition, operation and maintenance costs are significant, according for 20 to 23% for onshore wind farms and up to the 30% for the offshore wind farms. This paper presents the development of automated system for the detection of anomalies in the wind turbines. A key aspect for optimizing the management and predictive maintenance of the wind farms. The standard distribution method we use data processing and autoencoder network to detect anomalies. The data we use in the study comes from Mustisha University. Basically, we are working with historical data of unit cell vibration in turbine, both when they are working well and when they are failing. The figures analysis include erosion on the blade surface, unbalanced and twisted, recording a wind speed of 1.3 meters per second. Figures show the relationship between times and amplitude of data set with heavily foul condition due to blade twists. This wind turbine is made of fiber reinforced polymers and features a solid core. Its blades have an adjusted angle of 60, optimizing performance according to wind conditions. The rotor and generator adjusted the rotor speed, allowing effective operation at wind speed of 1.3 to 5.3 meters per second. It can generate approximately 60 power, a voltage of 20. An autoencoder is a type of unsupervised neural network which does not require labeled data. Its operation consists of encoding the input data and compressing it into a lower dimension representation, and then restoring the information. Anomaly detection algorithm. The algorithm is divided into three phases. Phase 1, normalization. Phase 2, training to the encoder. Phase 3, detection of anomalies. In this phase, we standardize with data using the C-score method to ensure a normal distribution. First, we load the data and calculate the mean and standard deviation. We apply the C-score with the equation. On normalized, we segment the data into temporal sequence or live file, allow us to capture relevant temporal information for sequence analysis. In this phrase, we train the autoencoder with batch of 64 samples for 30 exposure using 10% of the data as validation set. The architecture consists of 4 layers, 2 convolutional and 2 disconvolutional, with a 128 and 30 neurons in each layer. This allows for efficiently information compression. We use a ReLU activation function on our layer and apply a mean absolute error as the loss function, along with L2 regulation and the 10% drop up to about over 50. To optimize the model, we use stochastic gradient descent and compile with ADA optimization, set to a learning rate of 0.001 and a mean square error loss function. In this phrase, we generate prediction from the trained data and calculate a mean absolute error using the equation, where n is the number of samples, g is the actual value, and GLV is the model prediction. We set a threshold based on the maximum may observed during the train. Some exceeding this threshold are identified as anomalies, allowing the detection of faults in the wind turbines. The test of result of the wind turbine anomaly detection model focus on the several key aspects. First, the number of heavily cases and detect anomalies and record. This data always used to evaluate the effectiveness of the model in identifying faults. In additional performance metrics such as prediction, recall, and phase 1 are calculated. The result of the blade imbalance fault detection algorithm revealed an about 20.5 detection anomaly, indicating a high capacity to identify potential faults with a precision of 94.22% and recall of 94.60%. The algorithm shows effectively identify real anomalies. In addition, the average processing time is only 4.91 seconds, allowing real-time diagnostic and facilitating the technical implementation of correctional measures. The result of the blade surface erosion fault detection algorithm indicates an average of 23.60 detection anomaly, demonstrating a robust capacity to identify faults. The accounting of the 94.63% suggests the most of identified anomalies are correct, whereas recall and 90% reflects on the effectiveness of the algorithm in detecting real faults. Therefore, the average processing is the 5 seconds. The blade torsion fault detection algorithm identified an average to 36.9 anomaly, showing a strong fault detection compatibility with an accuracy of 87.54% more defect faults are correct, though false positive I can be reduced. The curve of 88.5% highlights is effective in detection area faults. The advanced processing time of 4.81 seconds enables real-time diagnostic. This research to propose an algorithm for detection anomaly in the wind turbines that combines data processing technique with autoencoder neural network. This approach improves the representation of the case feature with the increase the network ability to capture relevant patterns. Validation of the model with the real vibration data demonstrate its robust and ability to generate anomaly pairing across the different types of faults. For future work, it is suggested to integrate additional variables such as a maintaining data and explore various network architecture and artificial intelligence techniques as further optimize fault detection. Thanks for your attention.